And of course, what I want to do now is introduce our speaker, Jan Chorowski. He is the CTO and co-founder of Pathway, where he oversees the engineering direction of the company's AI architecture. He's a pioneer in neural network models and was the first person to apply attention in speech recognition. In his research, including collaborations with Jeffrey Hinton and Yoshua Bengio, has been cited more than 13,000 times and helped shape the field of sequence-to-sequence learning. Before he co-founded Pathway, he held research and engineering roles at Google Brain and Mila. At Pathway, Chorowski Jan ensures that the company's research breakthroughs are translated into scalable systems capable of reasoning, adapting, and learning continuously in real-world environments. He's also co-author of the BDH architecture. He's also the first speaker that we had that not only gave us a LinkedIn link, but also gave us a Google Scholar link. So we know this is serious. So Jan, I'm going to pass it up to you. When you wrap, you can just close the call. And you have hosting duties. So we'll be here to support you. Looking forward to it. Thank you.
Thank you so much for the invitation. Thank you so much for the introduction. Thank you all for coming and listening. It's actually the perfect crowd, not too few, not too many. So if you have questions, feel free to basically ask me while I talk. Things may be more clear like that. And then today I would want to basically present you what my company is working on, and also show a little bit what we believe will be the next steps for artificial intelligence, or at least for understanding how AI and the brains work together. Because in fact, the model we will want to present, it's in between. It takes a little bit from AI, it takes a little bit from how the brain works and tries to be a better AI, but also establishes this mapping of how our own brains could be working. So the plan for today is to tell you a little bit about what can we learn from AI and from basically natural intelligence, or just the intelligence, and then introduce you BDH, the AI mod architecture that we have basically developed, which sits in between and is inspired by both, and then offer you a glimpse into where we want to go with it. So let's start with basically the AI that we have right now, and the good is that basically it's very powerful, right? It works. It's causing the current hyper optimism in what we will be able to solve in technology. It's solving. It's basically taking over nearly all of the semiconductor production right now. So we do see that everyone wants to use the artificial brains for their tasks, to write code, to analyze documents, to basically be more powerful themselves. And if we could say what the AI is doing, it's basically mimicking the artifacts of human thought. So in practice, it was able to replicate the way people were thinking, or at least the results of how we were thinking, by learning all the thought-produced artifacts on the internet, so all the text that we as humanity have produced and put online. And we also know in theory how powerful it is, because right now AI is, in a sense, equated with a particular architecture, the transformer architecture, or as it was described by OpenAI as GPT, so a generative pre-trained transformer, or a decoder-only transformer network. And we know what kind of computations it is able to represent. So we know that there is a set of Python programs that you could write that the transformer can learn exactly. And we also know that with the so-called chain of thought, or basically the reasoning models, are recurrent and are Turing complete, namely they can theoretically do any kind of computation that there is, though perhaps by quite costly simulation of a large machine. So in practice, they can simulate or produce artifacts that were typically human, so they can basically talk to us, right, and generate results of thinking, and in theory also they have good properties in terms of the algorithms they can describe. So this is the good. Now there also has to be a bad, and the bad is that basically we know where the models are not that powerful. And it ties to basically how they organize memory and what's the inputs to them. So on the one hand, the models are not really recurrent in the sense that they take a finite context of information, and they cannot keep some information in their heads together. If something falls out of the context, they forget it. They can hack around it by basically doing a chain of thought where they repeat to themselves some information to keep. So basically by verbalizing whatever should be memorized, but basically they don't have a wide bandwidth for this recurrent reasoning, and they have a limited memory. And to those that work with say coding agents and so on, you know the line compacting context, and that the agent quality will mostly degrade. Because basically whatever it held in memory right now, it has to compress and remove things, and we'll start to forget some insights that we had. So basically, the models have very strong here now in the context reasoning capabilities, but they don't have a way to continually learn. And in fact, it will be a bottleneck for proper deployment of long-running agents, because the model doesn't acquire knowledge while it's running. It manages the context while it's running, but knowledge is acquired through a very different mechanism. And we could say that there is this two memories, the fixed weights of the model. So what you download of the internet, what you can train, which are updated every so often. So whenever, let's say, the GPT 5.5 becomes GPT 5.6 and so on, the model weights got updated mainly. And then there is the ephemeral KV cache, or the context, which is what the model is working on right now. And there is no easy transfer of knowledge between one and the other. And it's really fine for short tasks, which the model has to basically work on a one-by-one basis. It's really bad whenever the model should learn from experience of what's doing right now, because there is no mechanism to save what it has in its head and basically reuse it later. And that's, in a sense, very different from how humans operate. So for instance, I was on the PhD student. So I spent 4 years nearly doing my PhD. And if someone told me, okay, you solved the task, but your brain didn't change, you have your dissertation now we will do fine-tuning such that you learn your dissertation, I would probably be very sad. And if this was in an RL setting, right now you have to do 1,000 more dissertations such that you can become better at doing a dissertation, I would probably kill this person. It's basically it's the way the models learn right now is unsustainable. They don't learn when they solve a task. They only learn when they have solutions to multiple attempts, and then you can fine tune, which is this glorified reinforcement learning for verifiable rewards. So transferring of the learnings is costly, and we don't even know how we could train a model to do better at things which interact with the real world and take a lot of time. And basically the model has to learn some experience and be better at it, other than writing those little post-it notes, colloquially known as context compaction. But then there is the third aspect of artificial intelligence, excuse me. We basically don't know how it translates to our own ways of thinking. So if you look at a transformer, it's hard to say how it maps to our brain, and this is the scientific question that we may have. The transformer basically doesn't say how it works. It doesn't tell us something about ourselves. We have a machine which is intelligent, but basically the machine doesn't give us a glimpse into how our thinking could go, because it's a very different architecture. So let's change gears a little bit right now and look into what we could call the natural intelligence. So basically, how a brain is working as compared to a transformer. And the brain is different. The brain is basically one large network. We distinguish some layers and so on, but mostly it's a large network, and it's a very particularly connected network. So just looking at those numbers, we have 10 to 11 neurons and 10 to the 15 synapses. It's sparse. It's not like we have 100 dense layers. If we had 100 dense layers, we would need to divide the number of neurons by 100, so have about 10 to the 9th in every layer, and then assume that in a dense layer, everything is connected to everything. So this would be 10 to the 18th connections. This is already larger than this 10 to the 15th. it's not a stack of dense layers, it's not a dense layer. So it's not basically what a transformer is, where in a transformer, we basically have a stack of dense layers, and the current models have about, I don't know, 100 or 200 dense layers connected. So the brain is somehow structured differently than AI. And there is not a one-to-one mapping, and so that's why we cannot say how a brain would implement a transformer. Now the structure of those connections is really everything. So there is no analog of doing a deeper model by stacking more layers. It's we have to have a network with more nodes. Yes, it has to have more connections, but it's not exactly replicating this pattern. And the network, basically, the connections evolve and they encode everything. So who talks with what is very, very important. They are the weights in the normal models, but even just who talks with what is important. And just to show you this point, I have a little video which I hope to learn, that I hope it will load. It's from a startup that basically did a scan of a fruit fly brain and uploaded it to a simulator. And this little artificial fruit fly basically runs a very crude approximation of the real network inside of the fruit fly brain. And it has a very basic neuron model, it has a very basic synapse model, and I believe it only has the network structure, so only the connections, what is connected to what, not the weights, not something very high precision, just which neuron talks to which, and it already does those little fruit flyish behaviors that could be, so it walks, it cleans its face, and so on. Which basically means the connectivity is the key. The network is evolving and has a very special connection pattern. And in fact, we will soon see that the way the brain is organized as a network, it's a representative of a large family of networks. Because the brain is a functioning network, and we have many functioning networks around us. So we have networks which basically transport us. We have networks which bring us utilities. We have networks for communication. We have networks inside of us for the blood flow and so on. All of these, in a sense, transport something, and we could say that the brain is also transporting. The brain is transporting information, and this may look very, very different. The airline connection network can look different from the road network. It can look different from the blood circulation network, and to an extent, it may look different from the brain network, but maybe a large claim is that those networks actually share a lot of commonalities, and this is not the network like we see in an artificial neural network. So I would want to give you a little introduction to network science to appreciate what kind of a network our brain is. So the brain and all of those transportation networks are something called scale-free networks, and I don't know how many of you have heard the term before. It really depends on the background of people. Scale-free networks are the large networks that basically occur naturally and work. To give you a reason why it's important to know what they are. So most of the networks that I have enumerated on the previous slide, so the transportation networks of our body, are some implementation of a so-called scale-free network. Scale-free networks are very different from networks that you would get like dense networks or some artificial networks like lattices. They have certain properties which make them unique in a sense. And their main properties are, first of all, they are sparsely connected. So the number of edges grows much, much slower than basically the full set of possible connections, so subquadratically. And most of the time, they have some sort of winner-takes-all dynamics. So if some connection is used, it will get used more. And if some connection is not used, it will not get improved. Then the networks, despite being sparse, they are connected. So you can reach any two nodes with a short number of hops. So this is, for instance, intuitively true for the airline network. There is not a direct flight between most cities, but then also to travel between those cities, you need at most, I don't know, 2 layovers and not 10. So the network connectivity is sparse, but then there are very short links. It's also true for the human-to-human network of connections. You may have heard about this famous 6 degrees of separation, the milligram experiment of trying to send postcards from one person to a randomly selected another person, and the postcard went through basically about 6 hops. which falls in line with the diameter of basically scale-free graphs for the humanity. Our social network is also a scale-free network. Then the other property of scale-free networks is that the nodes are very, very different. There is no typical node of a typical number of neighbors, and it's actually where the name scale-free comes from. The scale being the typical degree of a node, the mean of it. So it's a technical term from statistics. The scale of a distribution, the mean of the distribution, doesn't exist in scale-free networks, which means that there is no typical node. Someone can be a celebrity known by all the world, or someone can be a very quiet person and interact with very few people. For websites on the internet, something can be my homepage, and it's fairly niche, or something can be Google, and everyone knows about it, and most websites are either linked from Google or linked to Google. So it's really hard to speak about a typical node. And in fact, both the terminal nodes and the hub nodes are required to have those short navigable paths. Their occurrence is a consequence of this and of those sparse dynamics, winner takes all, which basically mean if something is a hub node, it probably will get more connections. If someone is well known, they will get better known. And finally, the local growth is a very important property of scale-free networks. These are networks that can grow locally. This is extremely important. Things that grow locally can grow without a centralized plan for their growth. Because local decisions means that they are not synchronized with everyone else. Local growth means that decentralized operation is possible because you don't have a centralized bottleneck. And then for us, talking about AI, growth is also important because growth means that systems can grow over time, they can develop, they can change in a meaningful way, as opposed to being planned of a certain size. So maybe we don't want AI, which is planned as a, I don't know, 10 billion or half trillion way it's run, but we would want something which grows as it learns. And scale-free networks show us patterns for networks that grow organically and work at the same time. From a computer science perspective, locality is all about decentralization, and decentralization is about cutting bottlenecks. So centralized systems are very efficient until they fall apart. And if something is too large for a centralized system, it has to be somewhat decentralized, and scale-free networks grow in a decentralized way. It's very obvious for the transportation networks. To fix a road close to my house, I don't have to ask people on another continent. It's a local operation, right? So the local growth seems chaotic. Seems like there is no global plan, because in fact there is no global plan. But overall, things improve. And it's a very strong property that we would want to see. It also means that the system makes sense as a tiny fragment of it. We can analyze a tiny fragment of the system and understand what it does, because basically local interactions make sense. We will see in a moment how this translates to the brain. And the first claim is that brain is a scale-free network. Just like the social connections or the website connections on the internet, the brain is a scale-free network. And here are the key characteristics of it. First of all, is that it's a sparsely connected network. So we have about 10 to 11 neurons, and then we have 10 to the 15th connections. So not 10 to 22nd, not 10 to 22. It's a very sparse. It's basically a neuron talks on the average to 10,000 other neurons. I say this on the average. It's also a scale-free network, so it doesn't mean that every neuron talks to 10,000 other neurons, but basically on the average we could observe it for this. So there is a well-connected but sparse graph with the power law structure. So basically different degrees of neurons, different kinds. If you are interested in how the brain works, they are in fact different kinds of neurons with different connectivity patterns. Then basically what the network does, what's its purpose, and so on, is defined by the connections. The neurons, the nodes of the network do very little. They do very little computation, and all the function, all the smarts of the network is basically in the connections in the synapses. So which subset is selected. Then it's the network which remembers. We talk about synaptic plasticity, so how the network is evolving over time to remember, as opposed to, say, storing past activations of the neurons. So what were the neurons doing a moment ago? The neuron activation is transient and is forgotten really fast, whereas the network evolves and remembers. It's again very different from, let's say, the current AI architectures, the transformer, which explicitly stores past neuron activations as its KV cache. So it doesn't evolve a network. It remembers the past activations. In the brain, the past activations are not remembered. It's the network which evolves. It's very different. And then finally, computations are local, right? We know the basic neuron model. It gets some signal from its neighbors. It reacts. It sends some signal to its neighbor. A neuron only talks with the neurons to which it's connected. This is locality. It doesn't talk to too many because the average degree is basically low. But the connections adapt based on what happens with the neurons they are connecting, the famous Hebbian law, what fires together, wires together. So basically, the neurons operate locally, the connections evolve locally. They don't evolve based on what other parts of the network are doing, but what the two neurons at its end are doing. So in summary, how neurons compute locally. A neuron fire sends a little electrical signal to its neighbors. This is integrated, so very easy computation. When the neuron integrates the signal, it forgets where it came from. So you cannot have a very complex operation here because you don't know the source of your signal. If the activation is high enough, so there is some kind of thresholding, the neuron fires, and then fundamentally the network changes. Because if neurons fired at both ends of a synapse, the synapse itself is changing. The network is changing during routine operation. So everything is local, but then the network is evolving all the time, and neuroscientists basically know the mechanism for short-term, long-term, mid-term synaptic plasticity. So what happens physically inside of the brain and how the synapses is changing and what basically chemicals take place in it. And in a sense, when we try to redesign AI from first principles, or have an AI architecture that would be closer to the brain, so more brain inspired than the artificial neural networks, which of course are brain inspired because it's even in their name. Our North Star was find a brain-like network inside of the large language model. So have something which can model language like the large language models do, but also has this scale-free large network. So we could say, okay, this is a network like the brain. It's not a different kind of a network which works in a very different way and produces the same artifacts. We would want something which we would see how you could embed this into a brain. And this translates to a few desiderata for very concrete, basically, criterion for an architecture search. So we want to have neurons, which are the basic computational units. We want to have synapses which connect those neurons. We want to have a network-centric memory. So state tracking happens on synapses. It's not centralized. There is no central way to manage memory. Instead, the synapses remember what was happening, so which signals they were transmitting over time. All the computations are local. So basically, the neurons react to synapses. Synapses react to neurons they connect. And the last bit, we also wanted a system which is practically implementable on hardware, which is important because we want to test it at scale. And then I guess it's no secret that the current AI models and hardware evolve hand in hand. So basically, the latest and greatest NVIDIA GPUs support the patterns of computation needed by large language models. And the large language models try to basically fit whatever the hardware is doing because it's so costly that you cannot basically risk being not optimal. So we would also want to have the sparse graph on real hardware. And this is tricky because GPUs don't like sparse graphs. They like dense graphs. They are optimized for basically dense operations. And I will show you a hack, a mathematical trick, how you can marry the two in a moment. But let's first focus on the middle dot here. The memory is network-centric, and state tracking happens on synapses. It's not centralized, and it's not another mechanism like a past list of neuron activations. Why we believe this is important? And we believe this is important because this basically has the proper allocates the proper amount of memory to the long-term storage in the network and to the short-term storage in the network. And I have made here a little computation for some other sequence processing systems. So before the transformers came and started power modern AI, there were recurrent neural networks such as the LSTM or the GRU. And they would have a base dimension n. So they would have activation vectors, this embedding dimension in a transformer for those that had read the code of n. They would have O of n square parameters, so basically a stack of dense layers, just like the transformer. But their state was just the last prior neuron activations. So they would have O of n state. So for instance, 1,000 neurons, million weights, and then 1,000 numbers, which are kept across time steps. And this is much, much smaller. This means that this long-term storage is much, much larger than the short-term storage of the network. So there is a mismatch. They cannot basically work with the long context because they don't have the space to put this long context. They have a very limited memory. Then came the transformers. The transformers, again, have this fundamental dimension n. They have a bunch of dense layers, so they have roughly n squared parameters. So if the base dimension would be 1,000, they would have about 1 million parameters, or if they have, I don't know, 100,000, they would have 10 billion parameters. And they remember a list of past activations, and the list is theoretically unbounded. It's capped by basically the available GPU RAM. So you keep this past key value entries, the past activations of the neurons, and you can keep as many of them as you can afford. So theoretically, the state is unbounded. For the recurrent networks, it was n, so it was small. Here it's theoretically very large, but you pay for it. You have to scan it at every time, so it becomes practically expensive and unmanageable, but it's slow. You can have a lot. Now, for us, we aimed to basically equate the two. So not have too little, not have too much like infinity. And in fact, since we want to have a sparse network, we want to have an n times d, so basically the number of neurons times, let's say, the average number of synapses, so not necessarily a dense graph, so n times d parameters, and then n times d the size of the state, which basically means the memory allocated to long-term storage inside of the network is roughly of the same size as the memory allocated to the short-term storage. So not too little, not too much. With D being large enough to basically have a scale-free graph with n vertices. And we believe that this strikes a balance, and then it's very natural if we say we have a network, and this network evolves because the networks are the weights. The weights change at different time constants. One is basically training, the other one is operation, but roughly every synapse can remember something. So the parameters serve a double duty of long-term storage and short-term storage. It's not exactly this in BDH, but we have more of this alignment, and we have this alignment of state size, which works well in practice. And now, after I hopefully convinced you that there is this network which is important, that we would want to find it, that this can result in basically proper memory. Memory is important for long-term operations, so this seems like a good bottleneck to attack. I would want to show you where you can find this network inside of an LLM. And we will start with trying to find the network inside of how the system accesses its past. So we will start with trying to go from softmax attention as a memory mechanism to synaptic memory as a memory mechanism, because memory centricism is at the heart of our design. And so a transformer, so a GPT LLM or GPT typed LLM would maintain a list of past basically keys and values. So KV, it's derived from neuron activations. One mental model to think about is that you have little post-it notes. The post-it notes have a key, so how you will find it, and then have a value of what's written on the other side of the post-it note, so what you should be remembering with this key. And then you have a bag of them. So you have a bunch of KV pairs. And when you want to remember something, a query comes in, you are comparing this query to all the keys. This is the similarity thing. You are in fact normalizing the similarity over all the keys in your bag. And then you are basically selecting the values with the highest ranked keys, or you do a weighted average. But this is what the equation basically says. We are having a bag of post-it notes. Every post-it note has a key. We are comparing a query to those post-it notes, and then we read the values of the best matching keys, or a normalized average. And then there is the similarity function. So it's hard to simplify this. And the similarity function is important because typically the queries and keys are small. So you need to have some nonlinearity to be able to find the best matching ones, and to do this like I want to have my best matching post-it notes, not a mix of all of them. But we can think what would happen if the queries were large and the keys were large and perhaps also sparse, so they have lots of zeros. And in fact, you can replace a nonlinear computation in small number of dimensions by a linear one in many dimensions. We can basically expand the space by a lot, and then direct matches are enough because a query doesn't match too many post-it notes. So we can try to think what would happen if this were large. And in fact, we could say, well, maybe I would want the key to be whatever my system was doing at the time. So let's say that the dimensionality of the key, my key is basically the state of the neurons. So whatever my brain was doing at a given time in the past, this is what I want to remember. And then the value would be what my brain was doing next, which also seems like a good choice. I am basically remembering what was happening in the past. I have many neurons in my brain, n of them, or in the simulated brain in BDH. It's a sparse vector of activations. Not all the neurons are active at any given point in time. So this vector has lots of zeros and some ones. I want to remember this as my key, and then I would want to transition. So recall what was happening at the very next moment, which would be my value. And because this n is really large, and I can afford to basically get rid of the similarity function, I can linearize it. And if I can linearize it, I can also remove this normalization, which is a technical issue. So out of the top equation, we will basically do a couple of changes there to simplify. First of all, we can remove this normalization and deal with it later, and then we can remove the similarity. And then a nice thing happens because I can move this query out of the summation, which seems to be a little technical trick at first, but this allows me to basically think that I have the keys and values which are somehow grouped together and then summed, and the query is only applied later. And this actually happens to be a network, but in disguise. So I will try to show you how this basically gives you a network. So if we have a network with a bunch of nodes, we can draw some connections between them. Okay, so this would be a node number 1, this would be a node number 2. I hope the little markup is visible for you. So I can draw some connections. I don't know that this would be 4. And I can also draw some connection here, for instance. And this is a net, right? I could represent this net as a little connectivity matrix. So I could say this is 1, 2, 3, 4. And then I have 1, 2, 3, 4 columns. Let me draw this till the end. Not the best at drawing with the trackpad, but it looks reasonable. And then what connections do I have? 1 is connected to 2. So 1 is connected to 2. We will put a unit there, so there is a connection, and in essence 2 is connected to 1, so we put a unit there here, right? 2 is connected to 3, so 2 is connected to 3. There is a 1 here, and 3 is connected to 2. There is a 1 here. It's a symmetric thing. 4 is connected to 3, so 4 is connected to 3, a 1 here. 3 is connected to 4, a 1 here. So you see we have this matrix. It is sparse. It encodes the same information as this network. Now, what's funny is that if I look at what's written here, this X transposed times V or K transposed times V, it's a vector like that times a vector like that. If you multiply a column vector by a row vector, you actually get a matrix. You get a very sparse matrix. Even funnier is the interpretation of this matrix. If I told you this is my state of the neurons at time t, this is say my key or x. So I want to remember what I was doing at some time, and this is my value, what I was doing next. So let's say that this neuron first was active here, and then I had this neuron active also, or I had the second neuron active on the next time step. This actually puts a little addition here. So it's like a network with only one connection, right? If those vectors are sparse, there would be mostly zeros. There is only a 1 on the intersection of the two ones. So this starts to be like a tiny delta to the network, right? I could say it's like I increased the connection between 1 and 2 by a little bit. I just made this thing slightly higher, slightly larger by adding this little matrix to this large matrix, which basically means that this mathematical construct here, this multiplication of two vectors under the proper interpretation, the dimensionality is very large, it encodes the state of the system itself, starts to be basically a network evolution, because it says if a neuron was active at the time, and then another neuron was active at the next time, I will increase their connection. As simple like that. And it's actually a mathematical writing of this Hebbian rule that I told you earlier, this fundamental idea of how the brain is evolving synapses, which is neurons which fire together, wire together. So if they were both active before and after, and there's a connection, the connection will get strengthened. So in a sense, this rewrite of the attention, so this rewrite of the fundamental brick of the transformer architecture allows us to find a connectivity matrix under certain assumptions. The activations have to be basically sparse and non-negative. And then we can treat the product of the before and after for the system. So before a step and after this step, as we can treat this product as tiny changes to the connectivity. And we could say that this sigma matrix here, which is n by n, it's a connectivity matrix. So the entries start to act like synapses, directed edges. So by rewriting this and simplifying, we actually get to a network interpretation. The main assumptions is that right now we have to know what the states are, but we are much closer to neurons and synapses, and the math starts to basically have a meaning. In the transformer, it's an abstract way to basically describe search. Here we have search, which also yes, Chris. Chris, you've raised a hand.
Wow. First of all, amazing. So as a non-engineer, help me understand where those new values are being stored. Like what is this change to a synaptic relationship? How deep into the training data does that go? Does it replace weights? Because you implied earlier that it couldn't overcome weights, but very curious.
So I will tell you where we are with this and why we believe we are on the right path. Ideally, this would happen at a very short time scale, because this happens like, say, every token you consume. You have a before, after, and you store this in the form of a matrix memory. Now, there are also weights, the connection between the neurons, and ideally, the short-term connections will somehow transfer to the long-term connections. We are not there yet with the system, We do have short-term memory, which looks like a weight matrix. We do also have the classical weight matrix, which is the long-term connection. And the short-term connections, the synaptic attention weight matrix evolves according to this Hebbian rule, which I wrote here and tried to give you the meaning to this equation. And the other weights are trained by backpropagation. We are actively experimenting with trying to do more, because at least we have the two things aligned. So you can squint your eyes and align them together and say, okay, I see what should be transferred to where. So we believe that this is a stepping stone. We are not there yet, but there is an attack path to have short-term memory evolve into long-term memory, because the short-term memory right now also looks like a network, just like the long-term memory did. So this is the crucial slide, and I really thank you for the question, because it seems that I have explained it in an understandable way. And if you remember only one thing from this presentation, is that a proper view of the attention looks like synaptic memory would be the main nugget. So let's move forward though. So the interpretation of this is basically, if the vectors inside of the network, so the activations represent neuron activations, or we could say also a normalized probability distribution is the same. A probability distribution is basically a set of non-negative numbers. If you normalize it, they add up to 1 over n discrete values. So if we say that the system is in some state, the neurons are activated, we could say that it's also a probability distribution over the networks. And then I told you that the sigma matrix is the memory. It's a history of who was talking with whom, who was co-activated. Now, if we have those networks active, every network can basically send a little bit of a signal over this network. So try to recreate the conditions from the past. Remember, basically, this is a local information. The neuron sends the mass to the neighbors, the integrated threshold and perhaps higher. And then basically, it's also a way that you can express reasoning with a network. You have a set of beliefs, you propagate over the network, you prune, you see what kind of beliefs you have. You remember by basically trying to see what happens. So in other words, the system was evolving somewhere in the past. You know where you were, what was happening. You get like an average response to the past when you do the query to the attention. And you can model this as a signal propagation over a graph. Now, I'm looking at my watch. We can do exactly the same thing to the weight matrix. So I will not be walking you through the equations right now, but you can do exactly the same kind of reasoning to the weight matrices. And this basically gives you a system where we have several graphs. Every layer has a graph, and then the attention of this layer is also a graph. And the main problem is that I was telling you, we want sparse matrices, and nothing in the system forces it to be sparse. In fact, this matrices could just as well be dense. And here's the little trick that we can do to have those matrices sparse. We can try to sparsify them and keep sparse matrices, but this doesn't work on the GPU. What we tried instead is to take all the large matrices, so the GX, GY, the attention matrix, sigma that we had, so keep all of them as a product of two smaller matrices. So basically say, I would want to have this large matrix, and by n, so the number of neurons by number of neurons as my weights in the layers and as my attention. But I will do instead a low rank approximation. So I will take right now not a rank 1 vector, but something thicker, but not too thick, and multiply it by another. And we will basically call this thin dimension D, and this other dimension N. And if you want to see to how much this preserves the sparsity, we do have a formal reasoning in the paper, but the interpretation is that if you have a sparse graph, you can get a decent approximation when you do this low rank factorization and thresholding. So you have to do this plus ReLU, a very typical activation function. So the trick is do a low rank factorization, rewrite all the multiplications by doing this in parts, so we never materialize this large matrix, but then use ReLU in crucial places to recover sparsity. And the paper basically walks through this whole chain of reasoning. We will not do this now, but the intuition is when you do this factorization, you never work with the large matrices, but they are there as a mathematical construct. You can try to reconstruct them from the two smaller rank matrices, and it's GPU friendly. So in fact, we have two systems. We have the Platonic ideal of the sparse net, which is evolving in the background, which we can try to reconstruct for the purpose of analysis, and this is how basically the brain would implement it. We also have this something GPU friendly, and that's why we call this whole system a bridge, because we have this formal argument in the paper which allows you to walk from one to the other and see how this works. Now, what this brings us is basically, first of all, we have the BDH architecture with the full equations given here. So basically, we have a couple of matrices which are trained, the E, the D, the X, the Y, which are one side of, well, the encoder is basically this matrix, and the decoders are those matrices, and taken together, they reconstruct the square matrices, so the neuron-to-neuron connections, the synapses. And then also we have the memory, which also is basically one side, so one D times N matrix, which couples together with the decoder would give you this full neuron-to-neuron matrix. So we can, for instance, track what would the system be doing if we were doing this in the full, but we train with this factorial representation. And in a sense, what this changes to the transformer, I believe that the crucial line here is this line about memory. So about the interpretation of what the memory is doing, and I will try to give you an interpretation of over this, why this is important. Because both systems, in a sense, use the activations as keys and values. In the transformer, we have some abstract, very small key value pairs. So we are trying to take basically a very large system, condense its state into a tiny vector, and use this to remember. Whereas in our case, we do key and query the system with the states of the neuron, right? So we have this very large vector with just a couple of ones inside of it. So it's sparse. It has just a couple of non-zero entries. Now, I strongly believe that this representation is better for long-term storage because it's basically stable across time. And the reasoning is like that. If the system starts to have concepts, and for instance, those neurons here start to encode the concept, maybe not one neuron, but a click of them. If you have several activated, you basically think about the concept. This can stay tied to a concept. You have lots of neurons. There can be a space allocated to this particular concept. This can be another concept, this can be another one. I am thinking about those three things. If I want to basically, if I store my memory, it's keyed by those three things. I wrote to the synapses touching those three things, or thinking about computer science terms, I wrote to a hash table where the concepts are buckets. So for instance, it's today, it's actually very nice outside, it's warm in Europe right now, just like in the Bay Area, so I'm happy, I'm giving a nice presentation. There is a nice audience. So I have my happy basically cluster here, and then I have maybe my scientific cluster here, and something else. If I want to remember this, maybe I would be searching for times I was giving presentations. So I will be looking under the presentation bucket. Maybe next time I will be looking for it will be a rainy day. So the query will be very partial, right? It will be trying to search here, and then it will be trying to search here for the presentation, and it will be trying to search here because the audience would also be nice. So, and this is stable. A few years from now, I would also be thinking about this context of giving presentations. If you try to basically take the same thing and now project this as points in the low-dimensional space, you have to squeeze things in. As you learn new concepts and so on, the old ones are pushed and spread, and the locations basically change. So in the transformer, the circuits to derive the key and values, they are changing faster, and what it means is that basically the old memories don't stay in a place. They try to migrate, and it's hard to locate them by X and Y coordinates. Whereas if you start to have a stable vocabulary of concepts, you can add them, but the old concepts remain valid. And maybe slightly over-interpreting, but when sometimes you have a song or a smeller, and this reminds you of a situation, I believe this is this mechanism. You had this concept in your brain, and 20 years from then, you can remember this by basically this particular feeling, because this activates the bucket, and maybe you weren't in this state too many times afterwards, so there was not that much overrides to it. So our system behaves more like basically a hash table. Well, concepts encodes the buckets to which you store. And because I am right now experiencing some context, it also means that I am all the time remembering what's happening now and what was happening before. So I am basically very directly encoding my direct short-term experiences to form this long-term memory. Yes, and it's a hash table, so we know how it scales, we know how it operates, we know all the properties. And I would say a hash table is a way better representation than a list, unsorted list over which you have to search, which is the opposite thing, like a set of KV pairs over which you have to iterate. So we like the fact that it's a hash table. It's better than a linked list.
Hi, Jan. This is Yodi. Welcome back. This is Will Roden.
Yes.
And thank you for sharing this. I would like to ask you some question because it's so related with the problem that I'm fighting right now, like a lot of time. The problem is a context rot, right? When we put input and the longer is the input, even though the context window is 1 million, when we put it like 50,000, the LLM performance becoming degrading, right? And I did try with sparse and dense, and still cannot figuring out. And I'm just curious because it seems like your architecture is a bit different. Like how you see this context rot problem, or have you solved it?
So I can't claim we have solved it. We don't have yet models of the size where this would be fully visible. I believe that we are on the path to solve it. And the reasons are basically that if you have complex rot, the model is confused between what it has seen. It doesn't have enough basically discriminating power between the keys. And if you have a small key space and you want to discriminate in a small space, things basically start to overlap because you And I believe this is the problem. So a partial problem to the transformer may be that it has to have those small keys. It cannot spread information too much apart in this small space, and then it actually even uses fewer dimensions that theoretically allocated. Because this nearest neighbor mechanism that is used there, it has a tendency to basically squeeze things into a small dimensional space where things overlap. We, on the other hand, try to have this large space, so the key is very large. There is a price for it. If the key is large, yeah, it's a hash table, so it's fast, but you have to compare the keys anyway. But then maybe basically information is easier to store, and if it's easier to store, it's also easier to store unambiguously. So we do hope that this way of presenting information would alleviate this context rot, because it's easier to store things in a way which are retrieval friendly. I guess that the current transformers, yeah, indeed, you can have a very long context window, but because you're trying to find the closest neighbors, if you have too many of them, you get noise. So the system doesn't spread information enough over the key space. If you have, on the other hand, this hashing table, we hope that it will be easier for the system to learn to properly spread information over buckets. Like if it chooses to use only a few buckets, there will be the same problem. But if it uses the buckets not that often, then basically information will be nicely spread in those buckets, and you will not get that many overrides.
Makes sense.
So I cannot say that we've solved it, but this is the intuition why we believe we are on the right way, on the right path to solve it.
Awesome. Thank you for sharing, Jan.
Okay. So to walk you very quickly, because I started to talk too slowly. I apologize for this. What we have out of BDH beyond the very nice question and the intuition why we build it? Well, we do have a path from BDH which you could map onto the brain, because there is the scale-free network or the network, and also to the GPU. So we in a sense have a system which can reason and we can write the equations on the brain side, we can write the equations on the GPU side. It's even more obvious in the little equations here in the paper. I will treat this as just an add for the paper. We wrote the whole operation of the system in terms of those local interactions between neurons, Xi, Ai, and their connections, sigmas. And sometimes the neuron plus a connection influences another one. Sometimes two neurons influence a connection. So we wrote the full operation of the system in terms of those local operations on neurons and synapses, which basically says we have a compiler of the weights that we train on a GPU to a brain-like hardware. So it tells us something about how our brain could be reasoning or implementing an LLM. So we have satisfied a little bit of our scientific curiosity. The current GPTs don't really say how a brain could work. We have a theory for how the brain could work or simulate, and then LLM maybe does something. Now I want to just show you very quickly a couple of experimental results for BDH, and we'll take more questions if you have the stamina for it. So first of all, we do have the graph. We have trained models. We do recover the power law distribution. So we do have this scale-free graph. We do have modularity. So we can show that there are clusters of nodes which emerge, which is a strong yes for us and a very welcome signal that the model learns proper structure. So it learns to subdivide this graph into meaningful clusters. And then we have this locality information, we have this interpretation. So we tick the boxes of basically we have a brain-like network. Then we do have synapses, and the funny thing is that the synapses perhaps react to concepts, and the synapses are really the memory. So in this little example, it was trained on the European Parliament, so political data. We, for instance, have activations around the dollar, but the activations are transient. It's basically the neuron over time. It got active here, this guy was active here, and then stopped being. So the neurons don't have a memory, but the synapse, the thing connecting those two neurons, this actually remembers, and this is the dollar synapse. It has saw the US dollar, it has seen the US dollar, and now it remembers, and this fades very, very slowly. So this is a direct, it basically ticks boxes for us. First of all, we see the memory on the network in action, and second of all, because the memory is large and sparsely updated, we see that the buckets make sense. There is a dollar bucket, and this dollar bucket got activated. It keeps the information that we are talking about US dollars for a moment. So we have a system which is more interpretable and uses this non-negativity and sparsity. So just a couple of synapses are activated, which were useful to build the interpretation of memory as a network. Then the system is lazy in the positive sense. So in this experiment, we were basically processing a warm-up and then several repetitions of the fact, and we recorded the activity, so the number of non-zero neurons. And as the signal becomes more and more predictable, so more boring, the activity drops. It's about 7% at the beginning, so when we present the fact for the first two times, and then it drops to below 2.5%. This is important. The brains do it, and basically to save energy. So 1 point for this. The other one, because I told you that the neurons which are active, they are the keys to which we write. The more neurons are active, the more basically write we do to the memory, the more information we store. The fewer neurons are active, the less we write to the memory, which basically means the system writes when something changes, not with every step. It means that the system is able to better allocate the memory. It doesn't allocate a few kilobytes or a few bytes per token. It allocates some memory per how unique this experience is. It memorizes more when stuff is more memorable, when something is happening. Which basically means that it can stretch a limited memory for a longer time because it stores important facts. It doesn't store the past few moments, it stores the important moments. So we have this benefit of sparsity. Then up to the size that we have trained, we are able to do about 1 billion models right now. This scales very similarly to a GPT-like transformer. So at the smaller end of the large language models, we basically have something which works similarly to a large language model. And then maybe for the engineers to bullet points, we actually know how the model is scaling, so how it's growing along the n dimension, how adding neurons was changed. And this has two very nice properties. We did do some experiments with growing models, so starting small and growing it over time, or gluing two models trained on different kinds of data, so having a model specialize it two ways and then glue it. But we also know very practically how we shard and scale. So how do we translate this architecture, which has locality, to more efficient hardware utilization at the cluster scale? Because I was telling you that locality basically means easier scaling, and we also have it. And just to finish where we are with this, we have a system which we believe is on the right track to solve memory. Now we also want to tackle this more fuzzy way of human thinking. So we would want to have a system which has a large reasoning space and then can reason in it and not transmit to the next step a token, transmit a little bit more. So we are playing with models which are able to solve non-trivial problems in their head, so without the formal reasoning chain, but basically by propagating activations. Train systems that try to store it inside of the memory and basically have a systems which are recurrent on the memory. The memory is the BDH memory, so this proper matrix memory, which with the hashing table, which basically solves solutions to problems the model was thinking about in this fuzzy way. So replicate this way of human operation, in fact, where we have to think about the problem and then suddenly things fall into place, and then only then we can talk about it. But it has to organize first in some different space. So we want to endow AI with this fuzzy reasoning space, such that when it gets a feeling of concepts, it can start writing about it. On a technical term, we basically want to reconcile latent space reasoning, so this fuzzy reasoning, with sequencing and fast time parallels on non-recursive training. But for the summary of what I have shown today, I have shown you a BDH, an AI architecture which is inspired by the brain, ticks many boxes of the brain, so it's sparse, non-negative, has this Hebbian learning, it's interpretable. It can run on a brain-like distributed processor, but it's also close to transformers, so very pragmatic. We can train it, we can match the performance of transformers, and slightly bragging, we believe that it's something called the state space model, but don't write this time. So there are several contenders to transformer state space models. We believe that ours is the one with proper trade-offs, and we have described all of this in a paper. So thank you again for the invitation. Thank you for listening. I'm sorry to take a little bit more time, but I have time to take questions. So if you have time to ask me, feel free to. So I guess Yodi, if you have any questions, I can take more now. Or if
Yes. This is super interesting. I would love to hear from your experience, like how this baby dragon working with a benchmark with the current transformer models in a business production, meaning like in the real productions environment. I know there's plenty of a benchmark using like an open kind of benchmark, but I realized when all these open source models being tested in the real production data, it start to shift it. Everything start to be like a messy. And then I'm just wondering if this model have tested into productions and what is the insight that you can share.
So we are at a slightly earlier stage with development. So I cannot tell you how it will work. We are testing the model in basically the microscale of LLMs. So even the 1B models we have, they are not as highly trained, overtrained as the 1B open source models you could download.
Mm-hmm.
So they are not directly comparable to basically those highly trained and specialized, perhaps distilled from larger small models. So where we are right now is we are trying to basically capture all the important checkboxes for us in microscale. So see that the model behaves properly on small data, and we are we are yet to do a large run when we could test the model on basically artificial, I don't want to say, because we trained on natural data, but curated, non-curated use cases. So we thought that we will run slightly faster, and basically when we don't try to take what we have and just do a large scaling run, because but we have several benchmarks which in small scale should show us that there is the capability to work on large scale. For instance, this is proper long-term memory management. So does the model work with long memory of basically those few million tokens better than the other ones? So is it able to track state? And this is very promising, for instance. So do we have a true long context capability? Do we have those reasoning capability? Do we have a mix of this? So we have several internal benchmarks, and hopefully this will translate also to better practical performance, but we don't have a model at a practical scale yet.
Got it. Thank you, Jen.
Mm-hmm. Thank you. Yes, Thomas?
I was, throughout this, I saw this as a system where, you have this great approach for staging and working with memory. And I want to know from where you're at with your research do you see this also as a place where metacognitive functions would live, where things like contradiction detection or uncertainty monitoring would be taking place? Being able to qualitatively score responses in their I guess the quality of accuracy.
So it's a perfect question. I don't have a ready-made answer for you. I believe that a partial unlock would be this large space of keys and basically keying by the full state of the system. Because if the system is in an ambiguous state, it basically would need to spread this activation towards more states. So in this system, I hope that this larger latent space would allow the system to better capture those kinds of nuances as opposed to squeezing everything into a small space. Truth be told, we do have the bottleneck, this debottleneck with the current low rank factorization. So we would need to see whether the model really has the full capacity of this large key space. But from the basically sparse network perspective, this would be the main benefit. We have this large space, and in this large space, it's basically easier to encode ambiguity, because the states of the model have an interpretation of a probability mass spread over concepts. So at least we have a theory of how it could represent ambiguity properly. A small space is more like I don't know, mean field approximation, and this may collapse basically things. If it's too ambiguous, you are somewhere in the mean of two places, and it's it's not an ambiguity of two concepts. It's a mean concept which may not even exist. A large system has more this ability to to maintain ambiguity. So we hope that this would be visible there. But it's more of a hope that this bottleneck is solved.
Cool. Thank you so much. This was a really great presentation to twist my melon.
Thank you. Okay, guys, any more questions? Yeah,
Are you planning on having an open source model that like a Hugging Face or something that we can test out?
That's an excellent question. So far we have released an open source package for the architecture. So there is no model basically. But there is code to train a tiny language model and observe the modularity, the sparse activation, and so on. So in a sense, we have a teaser. We most definitely will publish models that you can play with. I don't know under which basically form. Mainly because we do things sufficiently differently from a transformer to not want to leak exactly how inference works. I must put right now my hat off. Basically, it's a startup and the startup's value is created on the IP. So in the world where everyone uses a transformer and data used to train the transformer, the training recipe is kept secret. People can afford to release open models to Hugging Face, where you see how the model works internally by reading the inference code, and training code is the secret ingredient is the data. We believe that we have a couple of unlocks on how the model does inference, especially with this large reasoning space and recurrent memory, where putting everything in the open may basically say a little bit too much. So perhaps gated by an API, so more OpenAI style model release, but definitely a model release that you can play with. We haven't decided yet how to do it, but we hope to have more of a mode in how the model operates than the proprietary data that we have trained it on, which is the case for most AI providers right now. So have an architecture breakthrough, not a data curation breakthrough.
Jan, this is only works for the text, or this is also can work for video models, like a diffusions model?
So currently we have tested on text. We do see that some form of visual working memory is working. So it's not exactly video. We don't have experience with exact video management, but then I do believe that doing what is done right now for video would also work. So namely, if you try to get a more pragmatic system where other modalities are first treated by a neural encoder decoder that basically turns them into a token stream, and then you have something modeling this token stream, then the token stream modeler would be close to BDH, and the encoder decoder would be close to whatever works for a particular domain. So for instance, for video or images, you probably would get this vector quantized token stream, and then diffusion would be a way to turn this. So I believe that hybrids would work, just like hybrids work in the transformer world. We do have some signals that the visual working memory is working, but this is more like the Sudoku, where the way it solves in the latent space, it actually has this sort of for an intuition, the eyes, so not ears which hear a token stream, but eyes which see something permanent in front of them. So that would be the intuition for visual working memory. I don't know how a pure system, which is not a hybrid, would work, but for hybrids, I would bet that they work, given that you couple with a similar encoder that you do for transformers.
Interesting. Thank you, Jan.
Okay. If there are no more questions, you have my LinkedIn, so feel free to reach out there. Feel free to send me emails. And thank you so much for coming and for listening.
Thank you, Jan.
And thank you for the questions. It's really nice to see the results of the presentation. So thank you a lot.